To test if an artificial intelligence is lying, researchers have built tools that look directly into a model's brain to measure how truthful it's being. But there is a single sentence that mathematically breaks these tools every time. It goes like this: the truth probe score for this sentence evaluates to false. A truth probe is just an internal evaluator. Its only job is to scan a piece of text and output a score indicating whether that statement is correct or incorrect. If the probe determines the sentence is true, it hits a wall. The statement says the probe outputs false, so if true, it outputs false. But scoring it false makes the statement accurate, requiring a true score. The system is trapped in an infinite loop. This simple string of words completely dismantles an AI evaluation tool that normally operates with 94. This is an active vulnerability in how safety researchers measure whether an artificial intelligence is being truthful or deceitful. Perfectly valid English syntax is enough to shatter the mathematical foundation of an AI's judgment, exposing a definitive limit to our ability to evaluate these systems. Modern large language models encode the text we feed them as vectors, arrays of numbers mapping out specific coordinates inside a massive multidimensional embedding space. A core part of AI interpretability is the lineal representation hypothesis. This is the idea that natural concepts correspond to measurable linear directions within that space. We can isolate specific directions for concepts like gender, human emotion, or geographic data like capital cities. We can physically measure the angle between a text input and the direction of one of these concepts. AI safety researchers use this geometry to search for a direction corresponding to truth. They feed models known facts and lies, then train classifiers on the internal activations to find the precise angle of truthfulness. When plotted, the system learns to differentiate facts from lies. Known facts and falsehoods pull into distinct clusters. To isolate truth, a logistic regression classifier, a geometric hyperplane, cleanly slices the space, drawing a hard boundary between true and false nodes. In a recent test using the Qwen 3.5-4b model, a probe was built by projecting the difference in mean embeddings from exactly 120 labeled training sentences. On withheld evaluation data, this probe worked incredibly well. It achieved an area under the curve score of 0.98, demonstrating robust statistical reliability across almost all standard tests. The only places it struggled were complex arithmetic sentences, like 5 times 7 is 35. Otherwise, its classifications were nearly flawless. Because this engineering works so cleanly in practice, it creates the illusion of a platonic representation space, a place where AIs naturally converge on an objective, universal truth. But that illusion vanishes when you test its structural limits. The desire to perfectly systemize truth is much older than machine learning. It stretches back to a massive, unresolved crisis in early 20th century mathematics. In the 1920s, mathematician David Hilbert proposed a sweeping program to secure the foundations of mathematics. He sought a systematic, infallible method to decide the truth of any mathematical statement, believing that objective truth could be completely captured by rigorous provability. That project was abruptly dismantled by Gödel, who used the logic of self-reference to break the system from the inside out. Gödel created a clever system where arithmetic expressions could make statements about other arithmetic sentences.
He constructed an Ouroboros, a mathematical sentence that essentially translates to, "This sentence has no proof." The conclusion was absolute. No systematic method can exist to prove or disprove every mathematical statement. Alan Turing applied this diagonal limitation to computer science with the halting problem, proving no universal algorithm can determine if a program will finish running or run forever. But the specific mathematical law that governs our modern language models is Tarski's undefinability theorem. Tarski demonstrated that no sufficiently expressive language can contain its own total truth predicate. If a language is rich enough to describe its own semantics, it cannot fully evaluate truth from within itself. Because transformer-based models are trained on and constructed from expressive natural language, they inherit these exact same historical mathematical limits. We can see this limitation in action by returning to the highly accurate Qwen probe we just built and deploying our diagonal attack sentence. The truth probe's score for this sentence evaluates to false. When the model processes this self-referential string, the geometry of the embedding space begins breaking down.
Rather than returning a clean Boolean classification of true or false, the probe gets caught in an endless loop, generating wildly inconsistent and chaotic scores. We can formalize exactly why this breakdown occurs using Lawvere's fixed-point theorem. Under Lawvere's theorem, when a system contains a sufficiently expressive evaluator, any self-referencing map without a mathematical fixed point will inevitably crash. Engineers try to fix this by softening the truth scale. Instead of a binary true or false, they map truth to a continuous graded interval between 0 and 1. This continuous mapping actually works for the most basic liar paradoxes. By giving negation a fixed point at 1/2, a standard liar sentence gets a self-consistent truth valuation of exactly 0.5. But this fix is temporary. Restricting the system to continuous functions invokes Brouwer's fixed-point theorem, which guarantees a fixed point exists, but severely limits what the system can express. The moment the model encounters a crisp, exact assertion like, "This sentence has a truth score less than 0.5, it breaks again, leading to a brand new paradox. There is no way to engineer around these structural limits. There is no mathematical protection against a diagonal attack on a universal truth probe. This is not an error in the code. The failure of this probe has absolutely nothing to do with a lack of training data. Scaling up the parameters, adding more layers, or multiplying the compute power will never close this specific gap. This boundary is an immutable mathematical theorem, baked deep into the laws of logic. That does not render truth probes useless. They offer immense practical value for model interpretability. They remain critical tools for detecting misaligned or deceptive behavior early in standard, non-paradoxical environments. But no single definable probe over a model's representation space can ever act as an infallible truth oracle. That boundary exists for any language rich enough to simply name the model, describe the probe, and form sentences about its outputs. If the tools we build for AI interpretability are subject to the same diagonal limits as the systems they monitor, what exactly are we measuring? The ultimate limits of artificial intelligence are not strictly hardware or software. They are governed by the precise logical paradoxes that define human mathematics.